Empty space isn't empty. Forget everything you thought you knew about nothing. Seriously, take the most perfect, pristine emptiness you can imagine. Go beyond our atmosphere, past the planets, beyond the sun, and out of the galaxy. Flee past the furthest quasars until you reach the cold, dark, intergalactic void. Now, pump out every last atom, every stray particle, shielded from every single photon of light and every whisper of radiation. You are now left with what? The classical answer, the one that feels intuitively right, is absolute, pure, unequivocal nothingness. A perfect vacuum. A silent, featureless stage where the drama of the universe plays out. But here's where physics performs its first great magic trick, or perhaps its greatest heist. That perfect vacuum, that absolute nothing, is a lie. It doesn't exist. In the strange and wonderful world of quantum mechanics, what we call a vacuum is, in fact, one of the most complex, dynamic, and seethingly active places in the entire cosmos. It is a cauldron of furious, fleeting creation. To understand this, we have to grapple with one of the pillars of modern physics, Werner Heisenberg's uncertainty principle. Most of us have heard of it in the context of position and momentum, that you can't simultaneously know exactly where a particle is and exactly where it's going. But there's another, even more profound version of this principle. It links energy and time. It states that you cannot know the exact energy of a system for a specific, infinitesimally short slice of time. There's always a fundamental fuzziness, a built-in uncertainty. This isn't a limitation of our measuring devices, it's a fundamental law of nature. The universe, at its most basic level, operates on a budget of probabilities, not certainties. Think of it like a cosmic bank account for energy. The law of conservation of energy is the bank manager, and it's very strict. Energy cannot be created or destroyed. But the uncertainty principle is like a loophole in the banking code. It allows for tiny, ultra-short-term energy loans. For an incredibly brief moment, an amount of energy, let's call it delta E, can be borrowed from the vacuum as long as it's paid back within a vanishingly short time, delta T. The more energy you borrow, the faster you have to pay it back. The universe, it turns out, is a high-frequency trader, making trillions upon trillions of these energy loans every single second, everywhere in space. So what does this borrowed energy look like? It manifests in the most spectacular way imaginable. It becomes particles. Thanks to Einstein's famous equation, E equals mc squared, we know that energy and mass are two sides of the same coin. Give the universe a little bit of energy, and it can create a little bit of mass. This borrowed energy bursts into existence as a particle-antiparticle pair, an electron and its antimatter twin, the positron, for example. These are called virtual particles. They are the physical evidence of the universe's ongoing heist. They erupt from the void, exist for a fleeting moment dictated by the uncertainty principle, and then they find each other and annihilate, paying back the energy loan to the vacuum in a tiny puff of energy. This process is happening constantly, everywhere. The empty space in your room, the space between your eyes and this screen, the vast voids between galaxies, it is all fizzing with this ghostly dance of virtual particles. Physicists call this seething chaos the quantum foam. It's a beautiful and accurate description. Imagine looking at a vast calm ocean from a satellite. It appears perfectly smooth, a uniform sheet of blue. That's our classical view of the vacuum. But if you zoom in, way in, down to the surface, you see it's not calm at all. It's a churning mess of tiny ripples, waves, and bubbles that form and collapse in the blink of an eye. The quantum vacuum is the same. It is a turbulent ocean of potential, a landscape of constant fluctuation. This baseline level of activity, this minimum possible energy that a system can have, is called the zero-point energy. Even at absolute zero temperature, where all classical motion should cease, this quantum dance continues. The universe can never truly be still. It can never truly be empty. The very fabric of reality is woven from this constant frantic borrowing and repaying of existence itself. This is the stage for our heist. We have a source of endless, albeit fleeting energy. But can this ghostly, ephemeral activity ever produce something real? Can this quantum foam, this zero-point energy, ever exert a tangible, measurable force on our world? The answer is a resounding yes, and it leads us to one of the most astonishing discoveries in all of physics. The Casimir force revealed. So, we've established that the vacuum of space is a lie. It's not a placid void, but a roiling, bubbling soup of virtual particles. A quantum foam of energy being constantly borrowed and repaid in an endless cosmic heist. This is a fascinating, mind-bending concept. But for a long time, it was just that, a concept. A weird prediction of quantum field theory that seemed to have no connection to the macroscopic world we inhabit. How could these ghostly particles, which exist for less than a trillionth of a second, ever add up to anything real? How could you possibly prove they exist? The answer came not from a cosmologist staring at the stars, but from a Dutch physicist named Hendrik Casimir, who was working at Phillips research labs in the 1940s. He wasn't trying to solve the mysteries of the universe. He was studying the mundane-sounding van der Waals forces, the weak attractions that exist between neutral molecules. In the process, he stumbled upon the smoking gun, the undeniable proof that the vacuum is alive, and that it can push and pull on the real world. Here's the setup, and it's beautiful in its simplicity. Imagine you take two perfectly flat, uncharged metallic plates. You place them in a perfect vacuum and bring them incredibly close together. We're talking distances of mere micrometers, less than the width of a human hair. Now, according to classical physics, absolutely nothing should happen. They are uncharged, so there's no electrostatic attraction or repulsion. There's no air between them to create pressure. They should just hang there, motionless forever. But that's not what happens. What Casimir predicted, and what has been measured in labs with exquisite precision ever since, is that a mysterious, attractive force emerges from the empty space around them, pushing the two plates together. This is the Casimir effect, and it is the physical proof of our quantum heist. How does it work? It all goes back to the quantum foam. Remember that ocean of virtual particles popping in and out of existence? These particles come in all different wavelengths and energies. Out in the open space, on the underside of the two plates, the vacuum can churn away, producing virtual particles of every conceivable wavelength. Long waves, short waves, and everything in between. These particles bombard the outer surfaces of the plates, exerting a kind of quantum pressure. Now, let's look at the tiny gap the plates. This gap acts as a resonant cavity. It creates a physical boundary condition. Not all wavelengths can exist in that confined space. Only virtual particles whose wavelengths fit perfectly into the gap a whole number of times can exist there, much like how a guitar string can only vibrate at specific harmonic frequencies. All the longer wavelengths are excluded. This is the key. Because many possible wavelengths of virtual particles are forbidden from appearing between the plates, there are, on average, fewer virtual particles in the gap than there are in the space outside. You have the full, unrestrained fury of the quantum foam pushing on the outside of the plates, and a calmer, restricted version of the foam pushing on the inside. The result is a net pressure imbalance. There is more quantum pressure pushing the plates inward than there is pushing them outward. And this pressure difference manifests as a real, tangible mechanical force. It is a force conjured from the vacuum itself. A classic analogy helps to visualize this. Imagine two large ships floating parallel to each other in a very stormy sea. The sea is raging with waves of all sizes, coming from all directions. These waves represent the virtual particles. The powerful, long wavelength waves crashing against the outer hulls of the ships push them toward each other. But in the narrow channel between the two ships, the ships themselves act as a breakwater. The long, powerful waves can't form or propagate in that small space. Only smaller, choppier waves can exist between the hulls. Because the wave pressure from the outside is greater than the wave pressure from the inside, the two ships will be pushed together. This is exactly what happens to the two plates in the vacuum. The Casimir effect is the universe's receipt. It's the tangible evidence that the zero-point energy isn't just a mathematical quirk. It's a fundamental aspect of reality, a source of real force. This isn't just a lab curiosity. It has profound implications, from nanotechnology, where this force can cause tiny machine parts to stick together, to the grandest scales of cosmology, where this same vacuum energy is the leading candidate for the mysterious dark energy that is accelerating the expansion of our entire universe. Physics' greatest heist is happening all around us, all the time. The universe is constantly pulling force, energy, and reality itself from the very fabric of nothingness.